Now we can turn our discussion from enols to enolates. And when you hear the ATE term, you need to think negative charge. So before we see how enolates are formed, let's just look at a very simple enol. Well, the corresponding enolate will just have a negative charge on the oxygen instead of a hydrogen. So the way that enolates are formed, they're formed when a base removes an alpha proton. For example, if we take acetone, and then let's explicitly draw in an alpha hydrogen, that's relatively acidic. pK of that's about 20. If you take a base and add to this, that alpha proton's the most acidic proton in the molecule. So what will happen, that base will take that proton and we'll put the negative charge on the alpha carbon. This is one enolate resonance structure, but we can, of course, draw the other resonance structure that looks more like the enolate up above. Of these two, this resonance structure is the major resonance contributor. But we can use the minor resonance contributor here to think about the reactivity of the enolate. And what we find is that this carbon with the negative charge on it, right here, that is a nucleophilic carbon, or a nucleophile. So we're going to be taking advantage of the fact that we can form this nucleophilic enolate, and then we'll add an electrophile to it to add things at that position. Just to give you an idea of a couple common bases that we'll be using here. We may use something that's a bit weaker, like sodium hydroxide, where hydroxide acts as the base, or sodium ethoxide, where OET minus acts as a base. Or we might jump up to something a bit stronger, like LDA. Which is lithium diisopropyl amide. Our cation is lithium plus, and then our base anion is this amide with two isopropyl groups. Remember that the amide term is given to the carbonyl functional group as well as just a nitrogen with a negative charge like this. This is a strong and bulky base. And we'll take advantage of that fact later in the chapter. We've talked about what an enolate is and how to form it. So now we're going to look at one of the more useful things you can do with an enolate, and that is an alkylation. So when you hear this alkylation term, think adding carbons. Specifically, we're adding carbons to the alpha carbon. There's two main steps in an enolate alkylation. One, we need to use a base to form the enolate. And 2, we need to add some organohalide. We'll just say Rx to put the R group at the alpha position. This step, we should note, follows an SN2 mechanism. So this is typically best when you're using an R group that is a primary or methyl halide. You can sometimes get away with secondary, but never tertiary. So let's look at an example of how we might do this. Here we have acetophenone, and we're going to do 2 steps. One, I'll add a base. I'm just going to use sodium hydroxide. Step 2, I'm going to add an organohalide. So let's say I want to add 3 carbons to the alpha position. So I'll use an organobromide with 3 carbons, propyl bromide. So now if we look at our starting material, here's the alpha carbon. It has 3 alpha hydrogens. We'll draw in 1 explicitly. Mechanistically, the first step is the base will come in and take that alpha hydrogen. That gives us the enolate. Generally, when doing these alkylations, it's easiest to just draw the resonance structure where the negative charge is on the alpha carbon because that's where you're alkylating. Next, we'll get to the product by adding the propyl bromide. So here's our alpha carbon. I'm going to number these 3 carbons here. That negative charge attacks that carbon, and you lose the leaving group. So be careful you don't lose carbons when you draw the product. We have our alpha carbon. I'm going to draw the new bond in red. That's bonded to carbon 1. And then we have carbons 2 and 3. So we've added 3 carbons to that alpha position. One place where sometimes people struggle when they look at this reaction is trying to say, well, why does this hydroxide deprotonate the alpha carbon instead of adding to the carbonyl carbon, like we've learned before where nucleophiles can add to that carbon? Well, it's not to say that the hydroxide can't add to the carbonyl carbon. But there were no productive reactions we learned where you add bases like this. So we added really harsh nucleophiles like hydrides and Grignard reagents, but not things like hydroxide and alkoxide. So does this happen? Sure, that can happen. But as soon as that intermediate forms, those electrons will come back down, displace the hydroxide, and reform the starting material. So it's not to say this step can't occur, it's just not a productive step. So the productive thing that happens is the base taking off the alpha proton, and then we do the alkylation.